Welcome everyone to Mr. Collier's set of notes on Newton's third law of motion. And this is kind of a fun one, and sometimes students love this one and struggle a little bit. There's a little bit of mind expansion going on here. Let's just start out before we talk about it. Let's label the page Newton's third law, law of motion. And this is one I'd like to put a little caricature over here. You don't have to do it, but it reminds me. So I'm going to put my best depiction of a canoe, because I always think that we get into canoe talks, and a little bit of water. And there's maybe old Isaac Newton. I don't know that he ever had a canoe, but he's paddling his canoe here. And if you're going to be in a canoe, you might as well have a smile on your face. All right, so here we go. Newton's third law of motion, the last of the three that we're going to discuss, is all about forces acting in pairs. I'm going to do a little autofocus there. And let's write the Newton's third law out first. So here we go. Newton's third law. And it says, for every, and that's a pretty big statement in science, all or for every. So for every action, and let's underline that because that's super important to what we're talking about here. For every action there is an equal and opposite reaction force. That's really an N. And so when you hear people kind of talking about this, they'll often talk about Newton's third law, action-reaction pairs, because it's always about action-reaction forces in pairs. That's what Newton's third law is all about. So here, let's just add a little to it right here. And let's say all forces act in pairs. Huge. That's huge right there. And let's keep going. Whenever a force is exerted, let's move it up a little bit, another force occurs that is equal in size. The fancy word we learned for that is magnitude, and opposite in direction. All right, let me just repeat that whole statement. All force act in pairs. Whenever a force is exerted, another force occurs that is equal in size or equal in magnitude and opposite in direction. So if you have one force vector, there's always an equal and opposite going the other way. All right, so here's some examples. And this will make sense to you, I hope. Example number one. If you have an action force, let's say is action force, that you sit on a chair, and that's something we've all done. I'm doing it right now. Your weight, and we know what that is now too, your weight pushes down on the chair. Pushes down on the chair. I think we all can agree on that. Easy. Here's this example. The reaction force to that, can you guess what it is? I think you can after our discussion the other day. The chair pushes back with a force equal to your weight. Pushes back with a force equal to your weight. You push down on the chair when you sit on it, and the chair pushes back with an equal amount of force in exactly the opposite direction. You sit down, push down, chair is pushing back up. Let's do another example. This one I think is also pretty familiar to you. You kick a ball. You kick a ball. That is the action force. The ball pushes back on your foot, pushes back on your foot, maybe your toe to be exact. That is the reaction force. That is the reaction force. All right? So you kick the ball kicks you back. I push on the wall pushes back. I have a baseball in my hand, and I throw it. As I push on the ball to get it to second base, the ball's pushing back on my hand with an equal and opposite force. This is a bit crazy. Now, there's one thing we have to make sure we write down. This is so important. I'm going to write important. And I'm going to underline it, and I'm going to make it an exclamation mark. Important. And we'll talk about this in a second. Action-reaction pairs. Action-reaction pairs act on different objects. And here's why we have to say this. If we were talking about this in class and I was giving this set of notes, some would raise their hand and say, but Mr. Collier, you told us that last week that balanced forces result in no motion. So if I kick the ball and the ball kicks back with an equal and opposite force, action-reaction pairs, the forces are paired, equal and opposite, then there should be no motion because the forces are balanced. And I understand why you asked that, but the thing is that when I kick the ball, I'm applying a force to the ball, and when the ball's kicking back, it's applying a force to my foot. So those equal and opposite action-reaction pairs are being applied to different objects. In the case of kicking a soccer ball, my foot and the ball. If I'm sitting on a chair, there's a force on the chair by my body, and there's a force on my body by the chair. So those equal and opposite forces are applied to different objects. The balance forces we discussed last week, and you did the force vectors for, were forces applied to the same object. And that becomes really important. And we're almost done. Let's write one more example. And we can certainly have more discussions about this point in class when we see each other. Our last example, and then we're done. If, oh my gosh, you guys, if you drop a ball, and we've all done this, we drop something, whether it's a ball or a glass or something, the force of gravity pulls the ball towards, oh you guys, this is so cool, the earth. I know, you're going, Mr. Collier, we know that. And let's just label that, that is the action force. Alright? But if forces act in equal and opposite pairs, if the earth is pulling the ball down towards it, what is the reaction force? Here it is. Let's write this. But gravity also pulls the earth towards the ball. So the earth, you drop a ball, the earth pulls the ball down, and the ball pulls the earth up with an equal and opposite force. chew on that one for a little bit. Let's talk about it when I see you in class.